Have you ever wondered what's really going on inside your computer when you're, say, browsing the web, listening to music, and downloading a file all at once? It's not just multitasking. It's actually conducting this incredible, complex symphony of things called processes and threads. And these are the absolute building blocks that make everything you do possible.
Just look at this. A great way to think about it is that your computer is weaving this giant, intricate tapestry. Every single thing you do, a mouse click, a video frame loading, even a character you type, is a single thread being woven into this massive picture. So in this explainer, we're going to pull back the curtain and demystify how all this complex weaving actually happens.
Here's our game plan. First, we're going to meet the foundational unit, the process. Then we'll see how you can actually take control and wrangle them yourself from the command line. After that, we'll look at why processes kind of hit a performance wall, which leads us straight to our main event, the super lightweight and efficient thread. And finally, we'll see how developers put it all to work to build the fast, responsive apps we use every day.
All right, first up, let's meet the heavyweight champions of computing, processes. Every single program you launch, your web browser, your music player, literally anything, it all starts its life as at least one of these fundamental units.
So what in the world is a process? Well, simply put, it's a program that's running. The best way to think of it is as its own self-contained box. It's got all the code, all the memory, and all the resources that a program needs to do its job. And traditionally, this process follows just one single path of instructions, kind of like a car driving down a one-lane road. Now, here's the cool part. Processes aren't just some abstract concept. If you use a command line terminal, you can interact with them directly. You can actually become a process wrangler yourself. Let's just walk through a classic workflow. Imagine you're running a command in your terminal. That's what we call a foreground process. Now, if you hit Control-Z, you don't kill it, you just pause it. Suspend it right in its tracks. Then you can type BG, and that sends it to the background to keep on running, which frees up your terminal. Need it back? Just type FG, and boom, it's right back in front of you. It's basically a pause-and-play system for your command line tasks. And you've got a whole toolkit for managing these things. The jobs command will list everything you've got running in the background. Control-C, that's your standard stop what you're doing right now command. For more precise control, kill, plus the process ID sends a polite request for it to shut down. But for that one program that just refuses to close, well, that's when you bring out the sledgehammer. Kill -9. That's the final, non-negotiable shutdown command. So processes are powerful, right? But they have a fundamental flaw. As software got more and more complex, developers started hitting a major performance wall. Just creating more processes wasn't going to cut it. We needed something faster, something way more efficient.
And here's the core issue. First off, creating a new process is incredibly expensive for your computer. It's a truly heavyweight operation that forces the operating system to duplicate a ton of memory and set up a whole new set of resources from scratch. And second, processes are isolated from each other by design, which is great for security, but it means that getting them to share information is a real pain. You have to build these special communication pipelines, and they're often slow and clunky.
So this leads to a really important question. If every single little action required firing up a brand new, heavyweight process, our computers would feel unbelievably slow. So how does your web browser manage to load images, run animations, and respond to your clicks all at the same time without a hitch?
And the answer is threads. They are the elegant, lightweight solution that allows a single process to do multiple things at what seems like the same time.
So a thread, which you might also hear called a lightweight process, is a much smaller unit of work that lives inside an existing process. So instead of building a whole new house from the ground up, you're just adding a new worker to the house you already have. It's a totally new path of execution, but inside the same container. And this slide just shows the difference perfectly. On the left, you've got your traditional single-threaded process, just one path of execution. But on the right, inside that exact same process box, you now have multiple threads all running concurrently. It's the same program, but now it's doing more than one thing at once. And this diagram, this reveals the secret sauce to their efficiency. See, all the threads inside one process, they share the same code, the same data, and the same files. This is what lets them avoid all that expensive copying that processes have to do. But, and this is the crucial part, each thread gets its own private stack and its own registers. This is what lets them work on different tasks independently without stepping on each other's toes. Well, most of the time.
The advantages here are huge. Your apps feel way more responsive, sharing resources is basically free, it's way cheaper than creating new processes, and you can take full advantage of modern multi-core CPUs. But there's always a catch, right? Because all that data is shared, you have to be really careful to coordinate or synchronize who gets to use what and when. And that adds a whole new layer of complexity to programming.
Okay, so that's the theory. But how do developers actually create and manage threads in their code? For a lot of operating systems, like Linux and macOS, the answer is a standard programming interface called pthreads.
Now, pthreads isn't a program, it's a standard, a specification. Think of it like a common language, a set of functions and rules that different operating systems can agree to implement. This gives developers a consistent way to write multi-threaded code that will work across all sorts of different systems.
Let's look at the core function for making a thread, pthread_create. I know, it might look a little intimidating, but it's really just asking for 4 simple things. Number 1, a place to store the new thread's ID. 2, any special custom settings, which you can usually just ignore. 3, the name of the function you want this new thread to start running. And 4, any data that function needs to get started. That's it. That's all it takes to spin up a new thread. And managing their lifecycle is also pretty straightforward. Thread PT join is like telling your main program, hey, pause here and just wait for this other thread to finish its job. Thread PT exit is how an individual thread can say, all right, I'm done here, I'm clocking out. But you have to be really careful with the plain old exit function. That's the big red emergency stop button. It kills the entire process and takes every single thread down with it.
And this all leads to the ultimate payoff. In today's world of multi-core processors, threading isn't just about making an app feel faster, it's about achieving true parallelism. See, a single-threaded process can only ever run on one CPU core at a time, but a multi-threaded process can spread its work across multiple cores, letting it do multiple things, truly, simultaneously.
This leaves us with one final and really crucial question. If you've got all these threads running at the same time, all trying to use the same shared data, what's to stop them from creating absolute chaos? How do you prevent one thread from accidentally overwriting the work of another? Well, the answer is something called synchronization. It's basically traffic control for your data, making sure threads don't crash into each other. But mastering that complex art, well, that's a topic for our next explainer.